Yes, so today we're lucky enough to have Wayne presenting the topic, which is very, very interesting topic for today. So, Wayne, I will just quickly go through your maybe your first paragraph of your very, very rich bio, and then from there you can carry on with the presentation for the day. Wayne graduated with a BEng, electrical and electronics degree from Stellenbosch University in 2001, and he joined Nelson Mandela Bay Metropolitan Municipality. He assisted this very same load research program, which was NRS 034 with data gathering, and was also the project manager for the largest residential rollout of ripple relays for hot water load control. So you can see that the man has been part of the clan, if I can say that, for the longest time, part of the group for the longest time. And Wayne, thank you so much. You can take it from here.
Okay, thank you, Mr. Chair. I would also like to welcome my executive for renewable energy, Louis Hall. I see he's joined us, and my colleague Stella Mojaji is sitting within earshot of me. So just welcoming them as well, and thank you, Mr. Chair, for your kind words. Okay, so the title of my talk now is Going Off-Grid, the business case for off-grid industrial microgrids. I'm just going through the structure quickly. I'm going to talk about the the problem statement, the energy trilemma, which some of you might have heard of. What is a microgrid? Which might be news to some people, but just bear with me there. The microgrid feasibility analysis process. And then we're talking about a case study of one of the projects we're busy with. And then the analysis of energy needs, which is part of the case study, the identification of DERs, the techno-economic model and financial analysis, technical considerations which we've picked up, the risks, and then finally the conclusions. Problem statement. Problem statement 1, the reliability of the grid. Of course, as many of you all are aware, one of the main problems faced by many industrial customers is the reliability of the grid. And load shedding has been a reality with us from 2008. So most school kids have actually not lived in a world without load shedding in South Africa. And there are also other outages due to normal breakdowns of the network. Power quality and quality of supply is also a big issue. And these issues really hinder the ability of industries to basically do their work and to meet their commitments to their clients due to the loss of production, and it also leads to financial losses. Yeah, electricity costs have also gone up quite dramatically, and these increases are expected to continue. And we know that Eskom has also applied for further increases for the 2023 financial year and beyond. Problem statement 3, there's also the pressure to reduce the carbon footprint. It's because of low global pressure to improve the sustainability and to reduce the carbon footprint. There are also financial incentives such as carbon tax measures, as well as public relations incentives. Next item, the energy trilemma. The previous problem statements can also be paraphrased. Problem statement 1 can also be called energy security. Problem statement 2 is also energy equity, and problem statement 2 is sustainability. And this is known as the energy trilemma. And up to the recent past, it was very difficult to address all 3 of these problem statements together in the same microgrid. Normally, a compromise was needed. For a rural village, for example, energy equity would have been a priority, but for a military installation, energy security was paramount. And now, with the increase in electricity costs and the reduction in the cost of renewable energy as well as battery storage, and also with environmental pressures, the same microgrids can address all 3 problem statements. That, together with the increase in the limit of self-generation in South Africa to 100 megawatts, has actually opened more doors for industrial companies to go off-grid. What is a microgrid? Microgrid is a collection of distributed energy resources with a control system that allows them to work optimally together. And DERs can be made up of wind, solar, energy storage, such as batteries, combined heat and power CHP plants, which can be gas or diesel powered. And then you get different types of microgrid. A microgrid can be either grid-tied, islandable, or off-grid. A grid-tied microgrid can only operate with the grid. It helps to reduce cost and improve sustainability. An islandable system can continue to operate even when the grid is down. This improves reliability, and an off-grid system operates independently from the grid. The feasibility planning process that we follow follows this SATS standard 62898, which is an adaptation of IEC 628898. That standard title is the Microgrids Part 1, Guidelines for Microgrid Projects Planning and Specifications. We first do a needs analysis of your energy needs. And we identify the suitable DERs, the distributed energy resources, and we analyze the DERs. And then here we have supplemented this process with our own processes at Proconics, and we have a hold point here where we then present our report up to that point to our client. And then at that point, once the client has a buy-in, we carry on with the rest of the analysis. We then do the techno-economical evaluation and optimization using Homer Pro software. And then we have another hold point where we present these options to the client. And then only after that, once the client has buy-in, we carry on with the concept design, and we take it further from there. Okay, I'm now going to present our case study. We are currently doing feasibility studies for microgrids for 8 industrial customers. Our case study is for 2 neighboring customers, and they belong to the same group of companies. Yeah, the first customer is a 24/7 operation, and the second customer is only on a day shift at the moment. Both customers will be connected to the same microgrid. Here is a load profile of customer 1. Now, this data, being industrial, usually it is fairly easy to get data, but you find that there are sometimes gaps. So we had to clean up this data to fill in missing data. The load is quite random, so we could just copy and paste the part of the load and fill in the gaps that way. The load factor is about 92%, which is extremely good. I made a histogram of that load, and you can see that the loads are in a fairly narrow band. And you might recognize this as being very close to a beta distribution. Customer 2, you can see there's a lot more variation in this load profile. There's the typical daily profile as well as a weekly profile. And the maximum demand is about 2,800 kilowatts, and the load factor is only 50%. Yeah, I also prepared a histogram of this load. But now, when you take both customers together in one microgrid, this is what the profile looks like. And the variation is a lot less as a percentage-wise. So the total demand is then, the maximum demand is about 8,500 kilowatts, and the combined load factor is 81%. So this results in a much better utilization of the electrical infrastructure than with only the customer 2. Okay, here's the histogram for the entire microgrid for the load. Part of the in analysis of energy needs is gas consumption analysis. Both customers use gas for process heating, but our detailed analysis was done by our internal process engineers, and this is outside the scope of this presentation. There are also several electrical chillers to produce chilled water, and the idea is that it is possible to replace them with absorption chillers, which can use heat from the CHP plant. Okay, identification of DERs is the next point. Yeah, various DERs were looked at. Solar PV, battery energy storage, and combined heat and power were found to be the more suitable options. Gas-powered CHP is attractive as customer one has a piped gas supply at a competitive price due to their very high gas demand. With gas, it's a bit like electricity in that if you use more gas, your gas demand is higher, then you can actually get a lower tariff. We did a solar PV assessment as part of this identification of DERs. Customer one only had about a 900 kilowatts of solar capacity, and customer two had a large roof area, and their solar capacity is 3.8 megawatts. We did separate studies using a dedicated PV tool. It was Helioscope. And in analyzing the battery energy storage system, we used budget prices which we obtained from suppliers. Yes, the combined heat and power, and the CHP plants offer an alternative way for companies to meet their thermal and electrical requirements. You find that your overall efficiency is a lot higher. You can typically get between 80 and 90% efficiency for heat and electrical combined efficiency. And so you can either use a gas turbine or a reciprocating gas engine, and it produces exhaust gas at a high temperature, jacket water and oil that's at a lower temperature, after cooler water and ventilation air. Now that can be used for heating, for hot water. It can produce steam, chilled water through an absorption chiller, and hot air. And there are various applications for this. It can be a replacement for an existing boiler in a plant. Next slide. The techno-economic model and financial analysis. We performed simulations on the system using different combinations of energy sources and storage on an hourly basis for the entire project lifetime. And we calculated various economic figures that are used for ranking the different options and comparing with the base system. And this was largely automated using Homer Pro software. We had to use spreadsheets as well. We couldn't always use the software for everything, but at least the software helped us to a large extent. This is a schematic of the microgrid that we built in the software. We had separate electric loads for the two different customers. Here's the solar PV system, gas gensets, and we took the thermal loads and put them here. There's actually a thermal bus bar that comes from the heat output of your CHP plant, and your existing boilers tap into it. Here we have the BESS system, the battery storage system, and it is modeled as a converter and the battery storage. Yeah, I put the chiller loads in as well, and all the existing boilers and burners in the plant are modeled by this boiler there. The customer one electrical load. This is how it is represented in Homer, and it is you can see it is quite a constant load and but with random variations. There are some points where the demand is lower, and this is, interestingly enough, the one is here at New Year's Eve, and then there's also one just before the plant before people returned from leave. Now, Homer actually makes all the years start on a Monday, so it shifts the data across. So that is why New Year's Eve is actually not at the end of the year, but in the beginning, a few days later than the 1st of January. You can see here how the profile is very constant. But now, on the other hand, this is customer 2. It has daily load variations. I didn't explain it earlier, but on the y-axis represents the time from midnight, noon to midnight, and again. And the x-axis is the day of the year. Here you can see that there are definitely there's lower load over the weekend, and also you have here the Easter weekend, which is this blue band over here, and of course you have the holidays as well, where the demand is lower. In this case, there was missing data in the middle of the year because of the riots that there were in the country at the middle of last year, and I also had to just fill in that data. These black lines over here represent load shedding and other outages. This client's electrical load is lower than customer one's. This one is subject to load shedding, whereas the other one is not. Here is our analysis of our results, and you can see there's quite a big reduction in operational expenses from having the non-microgrid option to having it with a microgrid. Your net present cost also reduced by probably about 25%. Your carbon emissions have more than halved, and your LCOE, your levelized cost of electricity, has also reduced by about a third. We calculated the internal rate of return. It was about 23%, and the payback period was about 5 years. Okay, now just some technical considerations, some points we picked up and learnings from this. For CHP microgrids, if the solar penetration is too high, it reduces the efficiency of the system. Now, this might sound counterintuitive, but because you are using waste heat from your generators as part of your process heat, you will have less process heat available if you throttle back your generators, if you have too much PV. So because we are looking at the overall efficiency, we need to take that into account. And unfortunately, the software helps a lot with that, because it can be quite a tedious calculation otherwise. We also found that with increased gas prices, battery storage becomes more economical. And if you still have a grid-connected system, it will only use generators during the peak periods, because if your gas is too expensive, it is still cheaper to run on mains electricity for most of the time, except for the peak periods, especially in winter time. In our analysis, we did not take into account the loss of production due to quality of supply issues or outages. And we can also find that a system which does not seem viable at the first glance, like if your IRR is 3% or something like that, or your LCOE is even higher than your grid tariff, it might still be attractive because your plant has more continuity and you have less losses of production. What we also found is with customer one, even though the customer itself is not load shed directly, the load shedding affects that customer, because the load shedding causes dips on the network, and that sometimes causes the motors to trip, and it causes the product to sometimes have to be thrown away. With a prolonged outage, there was even some of the product that hardened in the pipes, and that took a long time to clean that up, and with massive losses for the company. Yeah, everybody was, a lot of people we were talking to, including electrical engineers, were thinking that if you have a grid connected microgrid, you can actually smooth out your power dips. But we found that a microgrid of this size does not have enough inertia to smooth out the larger dips. You can use power electronic systems like a STATCOM, but they are quite expensive. And in our case, it was not feasible, but it can be considered for other applications. Also, if you use the existing electrical supply only as a backup, it's usually unattractive because of the network access charge and the other fixed costs that you still need to pay. Then we've identified some risks. Major risk is the limited gas supply in South Africa and the uncertainty of the future availability. Also, the unknown effect of major global events like the war in Ukraine on the price of natural gas, batteries, and all other equipment. Russia is a major supplier of some of the materials used in batteries, so that is causing a problem there in terms of the price. Step changes in the load, as well as PV output due to clouds, may cause instability in an off-grid microgrid when your renewable penetration is high. And you have a reduction in fault level, which requires the protection settings in the plant to be adjusted, and the grading will be harder in the plant, harder to achieve proper protection grading. The conclusions. Microgrids provide an attractive solution to improve the reliability of supply, reduce energy costs, and reduce the environmental impact of industrial electrical supplies. While there are advantages to remaining grid connected, for some customers, the risks outweigh the benefit. There's no single solution that is optimal in all cases for all projects and all microgrids. Each individual site has to be carefully analyzed. Off-grid microgrids are only feasible when piped gas is available and is at a competitive price. In our studies where piped gas was not available, it was not feasible to go off-grid with only PV and battery storage. Implementing a microgrid for a large industrial customer is a complex undertaking, and specialists from all engineering disciplines need to form part of the implementation team. There's a lot that electrical engineers don't know. Now, thank you, Mr. Chair, if we can open the floor for questions.
Yeah, thanks, Wayne. Very, very interesting presentation there with a lot of information. I was hoping that you'd get to some figures, though.
That is unfortunately intellectual property, and my
I
boss would
was
fire
really,
me.
really hoping that you'd get to some figures, but I think on my side, I understand, that obviously, the customer information, etc. And I hope that maybe when the project is completed and you have now agreed at that stage with the customer, you can mask their name, etc., and then you can just, even if the data is per unitized, something like that, at some point, if that can be available in future. But this is really great work. The detail in modeling and fairly a new subject. And on my side, I see there are some hands that are coming through. Just one of what I was looking for, what I was interested to see with one of the customers having such a flat profile, and also looking at the size of their operations in terms of the demand. It would have been interesting to see what was the size of that microgrid that would be able to supply that. As I'm saying, you said it's a 24/7 operation. So that means if you're putting a PV, then that PV needs to be available to supply the operations during the day, and also part of it must be storable in the energy storage so that at night you still have the same amount of power to supply the operations. Any comments just on that, Wayne?
Yes, okay. I did not make it explicit, but our solution is to have that total microgrid demand. The maximum demand is about 8.5 megawatts, and uh, we are using 2.3 megawatt gas generators, gas engines, reciprocating engines. So we are using 4 as a kind of a base load, and with a fifth one to provide redundancy. So we have about 9.2 to 11.5 megawatts of generation of gas generation, as well as about call it in the region of 3 to 4 megawatts of PV. And in some cases, we had some scenarios we found that it was feasible to put storage in, and others not. But yeah, it's quite a big microgrid.
Yeah, thanks, Wayne. Marcus, please go ahead.
Thanks, Wendy. When I'm part of the LCOE is, I guess, informed by what price outlook you have for grid electricity into the future. What view did you take there? That's part A, and then part B. Part of the LCOE is also probably linked to the model under which this microgrid would be operated, whether it's operated by the owner or an agent of the owner, or there are many different alternatives there for running the operations. Thanks.
Okay, what we assumed was a fairly conservative outlook. We assumed an electricity price increase of 8% per annum, which makes it conservative. So it means that if it in fact is actually a higher increase, then it improves our business case. Our client is in the process of forming a unit within the company to deal with energy. So this is all going to be run by the client itself.
Yeah. Thanks, Wayne. Mike?
Yeah, Wayne, excellent presentation. I think we're all going to be poring over your slide set to glean as much insight as we can from your very pragmatic approach to this particular project. It's not often that we get to hear about such data and the detail that you've gone through. I've got tons of questions, but I'll start with the 3 that are posted. You said that one of the plants had ran a couple of chillers. Did you look at thermal energy storage, ice storage, chilled water storage, rather than just batteries, electrical batteries?
No, we did not actually look at thermal storage because the chillers are quite small. Their current electrical load is only about 200 kilowatts. So in the context of our project, that is quite small.
And then likewise, in terms of the combined heat and power, did you look at perhaps storing energy from the diesel gensets or elsewhere in terms of hot water, something like that?
No, we did not actually look at that. Yeah, we had the process engineer also on the project. We have a team looking at it, so that did not. When they analyzed the process, that was not one of the feasible options, but it's certainly something to look at in some cases.
Okay, Wayne, last question. Yeah, I know we're running out of time. It seems to me that all good microgrid design actually starts with the lower level protection. If you look at the IEEE 2030.x standards as well on microgrid specification, commissioning, testing, there's a lot of focus on starting at the lower level with the protection. Did you involve any vendors such as Eaton or SEC or anybody in the from the protection side?
We are in the process of engaging with them, because we have 8 different sites we are looking at the moment. We want to standardize on one solution. So we are starting to engage with the vendors, but we haven't really come up with a solution to the final system yet.
Okay, Wayne, thanks a lot. Chair, over to you.
Thanks, Mike. It's very interesting. I must say, I think this integrated energy services modeling is just awesome. It's the way it's going to happen. Colleagues, we've got an expert here with a case study. If you have questions, let's hear them for Wayne. Thank you. Okay, I've got a hand up. Go ahead.
Hi, Peter Klein here. I just want to ask, a lot of these business cases are built around what the tariff structure is going to look like moving forward. Was there any consideration of any shifts from a standard megaflex to higher peak demand charges, and what influence would that have on the results?
Yeah, thank you for the question, Peter. Yeah, being quite pragmatic, because we are an EPC company and not the other meaning of EPC, engineering, procurement, and construction. We had to draw a line in the sand somewhere, and we had to work with what we know. This happened to be within a municipal area of supply, so for the tariff structures to change, and for Eskom to change, the Eskom structure tariffs to change, then the municipal tariffs have to change, and it will be a very long process, and there are many unknowns. So we did not take into account those extra or the proposed changes in the tariffs. Later on, we can run it as a sensitivity analysis when things get a little bit more clear, but we could get lost in analysis for weeks and weeks and not come up with a practical solution. So we had to just draw the line in the sand there. But it is an interesting thing to look at for future.
Great, thanks.
Thanks, Peter. Just from my side, I think you're asking an interesting question from an economics point of view. You're saying for municipal revenue recovery, are they going to shift the weighting of their tariffs? Is that correct?
Yeah, I think it was. I mean, I guess at the moment, a lot of the fixed charges are bundled into the energy charge on, say, Megaflex. And as more and more of those start getting unbundled from the energy charge, suddenly you might be paying the same or slightly less on energy, but suddenly your fixed charges are getting higher and higher. And if those get passed on to the consumer ultimately, that can make or break a business case down the line.
Yes, I understand exactly what you're saying. So it's that future view and where one gets that future view from is kind of important. Thanks. Mike, you have another question?
Yeah, Marcus, if I could just jump in here and reply to Peter, and probably, I'm sure Wayne has taken this into account. The great thing about the energy modeling is that you can start testing different scenarios with different approaches to the tariff. Look, microgrids, I believe, are going to play a big part in reducing the peaks, so that you have a flatter profile, which is far more attractive to the Munichs or the supplier. And I think there's a lot of interest. There should be a lot of interest, because it's a big thing overseas in energy flexibility. We still don't see, everybody is just completely focused on generation, but demand response, energy flexibility, I think is going to play a massive part. And I really do think with the work that Wayne is looking at there, he'll be able to test scenarios where you have larger tariffs focused on peak demand, and tariffs that reward a flat load profile. I'm not sure what Wayne has got to say about that.
Yeah, the problem is also, if the tariffs have to become more from a sustainability point of view for electricity distributors, the tariffs have to become more attractive, because if the electrical tariff is too high and it has too much of the demand charge is too high and things like that, then if a customer has access to a cheaper form of energy like piped gas, then they will defect from the grid. So I am very I can check various tariff scenarios that can be as a kind of a side project, and yeah, that is definitely something that we can take into account. Interestingly enough, we asked our client if they were interested in selling power back to the utility, and they were actually not interested, because many utilities, many of the Munichs will not actually let you sell back more than what you are using. And also because if you are selling back power, you are still subject to quality of supply issues on the grid. It's just an interesting note, also what we picked up.
Yeah, as you were talking, I was thinking as you have cost of supply studies in the industry, you probably also have the alternative from the customer's point of view, the cost to use a type of study, and that might inform lobby groups at NERSA when tariffing is going on. You may have another business here, Wayne. Mondi, your hand is up.
Yeah, thanks, Marcus. Now I'm back, but I think I will disappear so you can carry on like this. So I think just a very important and very interesting point there about the possibility of selling back, or the consideration of selling back to the grid. We actually observed something when we were as we are going through our own modeling of microgrids on our side, and we actually realize that if you are looking at an off-grid system, you basically you pretty much what comes from the generator, the PV, is what is required in terms of your consumption. So what I'm trying to say is, if your load, you've got a maximum of 8 megawatt of load, but then during a certain point in time, your load instantaneously is 5. That's what will come from your generator, because it will not, nothing more than that will flow, because that's what the load requires at the point in time. So then that actually became, and I want to get your comment on this one, Wayne, that actually became one of the shortfalls or the limitations that come with an off-grid system, that while your PV, which is, let's say, a 10 megawatt PV, is capable of generating more than 5 at that instance, your load is not more than 5. So therefore, then it has to remain, at 5. And when we looked at the levelized cost of energy, then the two scenarios, you could see a difference when you are selling back to the grid, as opposed to when you have got no alternative of selling back that extra energy. So that extra energy seemed to be playing a role, because when you are able to sell back, then it means when 10, which is your capacity of the generator, is available, you take advantage of it. But then when you don't have that, it means you will just only use 5, which now hits your business case. I don't know, what's your comment on that? Wayne?
Yeah, my comment on that is that your points are very valid, and that is, but I would say that is mostly if you have a varying load, like a domestic or a town kind of load. In our case, we basically have a base load. I know some people in this group don't like the word base load, but we basically have a base load of an industrial customer, and the generators themselves can basically generate with and supply the power without the PV contribution. If you look at the energy in the calculations, the PV contribution in terms of energy is less than 5%, which is different in a rural or a domestic kind of environment. So in this case, but what also helps the business case a lot is the fact that you can use your heat from your engines to replace existing boilers and burners in the process. But yeah, so and also with this specific plant, it's very rare that your energy supply, that your supply actually exceeds what your demand is. It's just because of the nature of this plant. But yeah, and also we don't really want to make the PV too big, because that reduces your thermal output of your generators. Even though our clients just want to put the PV everywhere, but it can also make the network less stable because of the variation in the generation. So yeah, what we find here is that the nature of the load very much dictates your architecture of your microgrid, and the business case that works for one scenario might not work for another one.
Yeah, great, thanks. Sorry, I see Mike has a hand up. Mike, carry on, please.
Yeah, thanks, Mandy. Thanks, Marcus. I think this is something that the entire group should be considering. When it comes to the inverters, are we going to start looking at grid forming inverters? And I think there's a lot of interest if you start looking at the IEEE 1547 standards. The feeling seems to be that any storage system, and I'm thinking of the larger storage systems, utility scale storage, that they should have grid forming inverters. And of course, we do have to remember that microgrids are intended to work with the grid. Then, the idea is never to seek to go off grid and remain off grid. That's just crazy. You've got to have microgrids that work with the grid. And that being the case, I think all of us as members of the Load Research Council should start thinking about where we're going with grid forming versus grid following inverters, and what standards should we be calling for. My biggest worry is that we've got people carpeting their roofs with PV and millions of little cheap inverters going in that won't support the grid. Microgrids have to function in a beneficial way with the grid, and how do we start pushing that? We don't want to end up with millions of microgrids that are going to just cause problems. I won't go into any more detail. I know we're running out of time, but the Australians at the moment are spending a lot of time focusing on the inverter side of things, and we just seem to be ignoring it. Thanks.
Yeah, if I could just respond, in this for this specific project, we are only looking at grid following inverters, because you'll never run your PV without the generators. So in effect, your generators form your grid, and then your PV will just connect to that. We have projects where we have no gas supply, so these gas engines are not feasible, and it will probably remain grid connected. And surely in that case, there will be battery storage as well as PV. So we will look at grid forming inverters in that case, definitely.
Yeah, thanks, Mike. You raised an important point, and that is the issue of basically customers leaving the grid. And I think that's where we came to the suggestion that this presentation be made. When you've put forward a case where it's there's a good business case for these customers to isolate themselves from the grid. And obviously the national challenge or threat in a way is where's South Africa going if the customers are fleeing the grid and no longer contributing, where does that leave the balance of customers that cannot leave the grid and the business case for that? I don't have an answer to that. It's just something to think about. I see a hand up. Is there any further question or comment from the audience? I see we've got a couple of guests in as well, new attendees.
If I can just quickly mention in the comment, I see Mike has shared a link to a short duration under voltage test, which might be of interest to the members. Thanks.
Again, Mike has put a LinkedIn group that you can join there, and is linked to the under voltage test in the comment section. So please harvest that before you leave, guys. Okay, Mondi, I think we're sort of coming to an end. Anything else from your side?
Yes, so just maybe a question or a comment. Now, there is another perspective of this, the microgrids technology, and the fact that now we are seeing more people starting to adopt microgrid as an alternative. There is the whole issue around the policy. When we started with the battery energy storage, the bulk grid scale battery energy storage, we initially thought that we would put that thing under, in terms of the grid code, we put it under maybe your inverter-based technologies and treat it as such. But then we later realized that actually, no, this is not a load and it's not just a generator. And so basically it is a storage and it plays certain roles, and we had to come up with its own, it had to have its own grid code. So what is your feeling in terms of, the whole policy, regulatory aspects, even the technical standards, when it comes to now, putting some governance into these technologies, this technology, Wayne?
Yeah, I think there are definitely gaps in the existing grid code. It's also debatable, and we've found this in a neighboring country as well, where you have a renewable energy source connected to an existing load. And now, must that whole combination be grid code compliant? That there's all kinds of questions. So I don't really have much of an answer there, but I know that there are some gaps there. There's also that Eskom standard for connection of embedded generators that is applicable, and some of the Munichs can also adopt that. Yeah, there are also different issues, like, for example, if you have an islandable microgrid, you can't have your generators dropping out or tripping on island. You can't have your anti-islanding tripping out your generators, or your PV inverters. You can maybe trip the main the buck breaker or something like that. But there are definitely, the regulations must actually catch up. But at the moment, we are trying to stay within the existing regulations. And that is also maybe one thing where it might be attractive for customers to go off-grid, because, that it might be easier for them if they don't have to be compliant with the various regulations, which is a possibility.
Yeah, thanks, Wayne. So I think, Marcus, just some concluding remarks from my side before I will hand over to you now to close as well. Thanks. Just want to say thanks, Wayne. This is actually a very, very critical area that you have touched, and I think we are going to aim at hosting a few of similar, maybe different aspects of this topic from different presenters. There is issues of tariffing, what sort of tariff would be appropriate for something like this, and that is another aspect of it. But I think from the technical side, the modeling that you have shared, definitely now that was a good contribution towards unbundling this whole topic. And I think, Mike, maybe at some point you might also want to prepare a presentation on certain aspects of this, even if maybe you come with just the standards that are existing elsewhere that we can take advantage of. Just a review of those standards and guidelines and best practices that are in existence. Maybe that will be another angle to approach this. But colleagues, thank you so much. Thanks for the contributions. Marcus, I think now you can close.
Yeah, again, Wayne, thanks. This was really a nice demonstration of integrated sort of energy service modeling and following through, linking it to grid codes, client needs, etc. Just lovely to see. So glad that you popped in to do this for us, and much appreciated. Colleagues, if there's nothing else, I will declare the meeting closed. Wayne, once again, thank you from our side, and we wish you well and hope to see more of this in future. Thanks.
Okay, thank you. Thanks, Marcus. Thanks.
Bye.